This is Daniel Coosbury, and we are continuing looking at some more complicated probability problems. And this video is going to introduce the idea of independence and show you what happens when we try to find joint probabilities, the ones that are using the word and conditional probabilities, when two events are what we call independent. So I'll show you what that means. If you haven't seen the video on conditional probability and the multiplication rule, I would go watch that one first because this is going to elaborate on a few of those ideas with conditional probability and the and probabilities that we get from the multiplication rule. So let's start by looking at independence. Two events, A and B, we're thinking of two events still happening together, are said to be independent if the occurrence of one event does not affect the probability that the other event will occur. So a few of the examples I looked at on the conditional probability video involved having two events happen, and one of them was conditional on the other, and if one happened, it affected the chance the other one would happen. Well, independence is like the opposite of that. So we're now thinking of two events that can occur, and one of them occurring doesn't affect the chance the other one occurs. So what that means mathematically speaking is that if two events are independent, then the chance that A happens given that B happens is just the chance that A happens regardless of B. So this conditional probability is simpler now because this is just the chance that A happens because B doesn't affect it at all. In the same way, the chance that B would happen given A happens is just the chance that B is going to happen regardless of A. So the conditional probabilities, you could say, don't really exist. Really what we're saying is the conditional probabilities are simpler. They don't really take the given thing into account when they're independent. If two events are not independent, we're going to call them dependent. And we're going to see this is going to affect how we do the multiplication rule. But first, let's just look at an example of some independent and dependent events. So here's some two events. We're picking a college student out of a group at random, and the events we're interested in are the student being a freshman and being less than 20 years old. So the question is, are these two events independent? Another way of asking that is, if you know that you have a freshman, does that affect the chance that the person is less than 20 years old? The answer is yes, because by and large in colleges, most of the students in the freshman class are going to be under 20 years old. They're going to be around from 17 to 19. And so we know that not every single freshman is under 20, but if we already know that one of these is true, does it affect the chance the other one's true? And the answer is yes. In the same way, if we were to know that our student was less than 20, does that affect the chance that we have a freshman when we pick this person out? The answer is yes. So these two events are highly related, and we know that if one of them is true, it's going to affect whether or not the other one's true. We're going to call these dependent events. So if we wanted to come up with a conditional probability, being a freshman, given that you're already under 20, that probability is going to be a little bit higher than if you were over 20. Now here's another one. We're picking a college student at random. The two events are the students born on a Sunday and they're taking a statistics class. So the question we should ask is, if we know they're in the stats class, does that affect the chance that they were born on Sunday? Well, no, that's ridiculous. If we know that they were born on Sunday, does that affect the chance they're going to be taking a statistics class? No, that's also ridiculous. This is an example of independent events. So oftentimes we can tell two events are independent because we know one doesn't affect the chance the other one happens. Sometimes we don't know and we're going to have to be told or we're going to have to inquire about it. But most of the time, at least in the problems we're going to look at, it's going to be pretty clear whether we're dealing with dependent events or independent events. So like I said before, if they're independent, these conditional probabilities reduce to just simpler versions. So notice how this B and this B are the same, this A and this A are the same. The given thing just doesn't affect the probability is what we're saying. This ends up leading us to a much simpler version of the multiplication rule. So in the previous video, we saw that the multiplication rule says the probability that A and B both occur is equal to the probability of A given B times the probability of B. And now we're saying that if these events are independent, then this is just equal to the probability of A. That's what we're saying up here. So the multiplication rule reduces to the probability of A times the probability of B because they're not related to each other. They're independent of each other. So we can just find their individual probabilities to get the joint probability, which is going to be really nice. So let me show you an example of this. Remember, this is only if they're independent. So in this problem, if we're going to use the simpler multiplication rule, we've got to make sure we know these two events are independent. So let's see if we can see how that works. Suppose a process consists of two sequential steps with the probability of a non-defective part being produced in the first step, we'll call that event A, being 0.95, and the probability of a non-defective part being produced in the second step, we'll call that event B, is 0.98. So let me kind of back up. We're imagining producing a product in two steps, and the chance of not messing up in the first step is 0.95. So 95% of these products are going to be non-defective after the first step, and 98% of the products are going to be non-defective after the second step. So this would be a 5% chance of producing a defective product in the first step, and a 2% chance of producing a defective product in the second step. And then this last sentence is the kicker. These two steps are independent. So this is how we know that we're going to be able to use the simpler multiplication rule, because these two steps are completely independent of one another. So if you produce a non-defective part in the first step, it does not affect the chance that you produce a non-defective part in the second step. So on that last video I made with conditional probability, we had a tree diagram, and the branches ended up having different probabilities based on whether the product was defective or not. This is not the case. So if you produce a non-defective product on the first step, you still have a 2% chance of producing a defective product on the second step. They're independent of each other. So the chance of producing a non-defective product at the end of both steps, let's see if we can write this in a nice way. We want to say that A is non-defective and B is non-defective. I'm abbreviating. So this is after both steps. We want both of them to be non-defective so that the whole product is non-defective. This is going to be the probability that A is non-defective times the probability that B is non-defective. That's because they're independent. So the reason I can take this and split it up into two separate probabilities, and we're multiplying these together, is because the two events are independent. And so I have both of these probabilities from this problem. The chance that A is non-defective is 0.95, and the chance that B is non-defective is 0.98. And so by multiplying those, I get my chance that I make an entire product without something going wrong. So I'm going to find that probability and do 0.95 times 0.98, and I get 0.931 as my answer. So there's a 93% chance that I produce a product that's non-defective. So your job after finding this would be answering the question, is this an acceptable number? Like having 93% of your products being non-defective means 7% of your products are defective, and is that acceptable, or should you go in and try to figure out how to make this number higher? What can you do? So that's an example of doing the multiplication rule with independent events. We didn't have conditional probability. We just had each separate one because they're not related to each other. They're independent. So the conditional probability doesn't really exist. I guess you could say it like that. Okay, so another nice application of working with independent events is there's a certain class of problems that we can do pretty easily, and I'm going to call them at least one problems. And this is going to use the idea that events are independent, and we're also going to use a complement trick that we looked at a few videos back. So here we have items that are expected for flaws by 3 inspectors. If a flaw is present, each inspector will detect it with probability 0.8. So imagine you got an item off the assembly line. You're going to hand it to inspector number 1, and they're going to check it, and then they're going to pass it to inspector number 2, and they're going to check it, and they're going to pass it to inspector 3, and they're going to check it. The inspectors are going to work independently, which means that if I say I'm inspector 1, if I say that it's fine, that's not going to affect what inspector 2 says. He's going to inspect it as though I've never looked at it. He's not going to be biased towards my opinion or against my opinion. So these are going to work independently. And the question is, if an item has a flaw, what's the probability that at least one inspector detects it? So maybe we're not interested in the inspectors doing it perfectly because no one can really do it perfectly, but we are interested in the defective items being caught. So all we really want is just one of them to detect it, or two of them would be fine, or three of them would be great, but we just want at least one. So we're going to find the probability at least one detects the flaw. And so here's the at least one trick, because this is kind of this can kind of get confusing if you start throwing in a bunch of like different events and calling them and whatnot. I'm going to do what I call the at least one trick, where I'm going to subtract, I'm going to do 1 minus the complement. So what's the complement of at least one person finds it? So this could be one person finds it, or two people find it, or all three of them find it. The complement of this is going to be that none of them find it. So none detect the flaw. And trust me when I say this is easier to find than at least one. This just gets messy because this could be one, or it could be two, or it could be three. This is a lot easier to find. This would be the probability that all three of them fail to detect it, which we can compute. So let me rewrite that none probability this way. This is the probability that the first person fails to find a flaw, and the second person fails to find a flaw. So meaning there's a flaw and we missed it. And the third person fails to find a flaw. So what you need to be comfortable with as I'm working through this problem is how I got from this first line to this third line. So we got the at least one finds the flaw, and then we did the 1 minus the complement trick. This is the complement. So this is at least one, this is none of them. And then I just rewrote this in this way. These are saying the exact same thing. None of them find a flaw, meaning the first person doesn't find it, the second person doesn't find it, and the third person. So there's ands here. And now I'm going to kind of expand on the multiplication rule that says if I'm finding an and I've got independent events, well, that's just going to be these three probabilities separate, all multiplied together. Let me write that out so you know what I mean. So I'm saying that since these are independent, so this equal sign comes from the fact they're independent. This is the probability that the first person fails times the probability that the second person fails times the probability the third person fails. So I just took these ands, these three events, and I broke them up into three different probabilities because they're independent. So I can do that. That's kind of like what I did here. I have this and that, and I just broke them up into two separate things because they're independent. And I'm multiplying these together when I get my final answer. And now that I've done all this stuff, and if you're not really clear how I did it, I'd go back and watch this part because this is the trick part. Now that I'm here, I can start putting numbers on here. So the probability that the first person fails to detect it is going to be, well, hold on. It says that they're going to detect it with chance 0.8, which means they're going to fail to detect it with chance 0.2. Okay, so this is the chance they fail. The chance they succeed is 0.8. The chance they fail is 0.2. The chance that the second person fails is also 0.2. The chance that the third person fails is also 0.2. They all have a chance of succeeding as 0.8, 0.8, 0.8. The chance they fail is 0.2, 0.2, 0.2. So this could also be written 1 minus 0.2 to the third power. And I'm going to find that on my calculator now. So 1 minus 0.2 to the third power is going to be 0.992. You don't like this third power part, you can just do this multiplication, then subtract it from 1. You'll get the same answer. So this is a nice example of kind of an expanded version of the multiplication rule using several independent events. So this is the independent part where I go from the ands to the multiplication. But I also use the 1 minus the complement trick. So when you see problems, and you'll probably see problems that say at least 1, This is how I would suggest do it. I would try to follow this scheme, do 1 minus none, and then see if you can break up those things. So this is a pretty complex problem, and it uses the multiplication rule for independent events. It also uses the 1 minus the complement event. And then this trick, turning none into all of them failing, is another kind of a trick thing. So I'd look over this problem a few times, but it's a pretty neat trick. And trust me when I say it's easier than finding this probability the way I wrote it down the first time. Okay, there's something else we should look at with the concept of independence. So when you're drawing two items from a population, there's actually two kind of broad ways you can do it. And depending on the way you do it is going to determine whether you're doing two things independently or whether one of your draws is going to be dependent on the other draw. And I've just got one example of this, and I think you're going to get what these words mean when I show you the example. But let me read you the definitions first. We can replace the first item drawn before sampling the second. This is called sampling with replacement. So imagine I've got 10 marbles in a bag or something, and I pull one out, and then I want to draw a second one. Sampling with replacement would mean I put the one back in before I draw another one out. So I put the one back in, there's 10 items again, and I draw another one out. That's called sampling with replacement. I'm replacing the first thing, I'm putting it back, and then I'm drawing again. The other option is to leave the first item out when sampling the second one. This is called sampling without replacement. So if I pull out a marble, there's only 9 marbles left. Then I pull out another marble out of the 9 that are left. That's called sampling without replacement. I'm not putting the first marble back. When sampling without replacement, each draw is made from the entire population. So that's the putting the marble back. I'm always going to have 10 things when I draw the next one, as long as I keep putting them back. So the probability of drawing a particular item on the second doesn't depend on the first draw. When you put the marble back, you end up with independent events. When you replace the item, you end up with independent events because you're throwing it. Your second draw doesn't depend on your first draw. And I'm going to draw a picture for you in a sec to show you what I mean. When you sample without replacement, your draws are not independent. So if I keep the marble, there's only 9 left, then that second draw is going to depend on what's in my hand from the first draw. So let me show you an example. This isn't really practical anymore. Now we just have balls in an urn, and I'm going to go ahead and draw a picture of that to show you what I mean. So here's an urn. Oh, there we go. And in my urn, I've got 3 red balls, I've got 4 blue balls, and I've got 3 green balls. And the idea is you're going to draw something out of the urn at random, so you can't see what's going on in here. You just reach your hand and you draw one. And I want to find the probability that I draw 2 red balls back to back. And I'm going to show you how to do that with replacement, or sorry, without replacement first, and then with replacement. And I want you to see how when I do it without replacement, I'm doing independent draws. So the probability I draw a red and a red is going to be the probability that I draw a red ball times the probability I draw a red, given that I already drew a red. Okay, so maybe I can just kind of visualize this for you. So I'm going to draw a red ball out first, and the chance that I draw a red ball out of this is going to be 3 divided by 10. There's 10 balls, 3 of them are red, so this first probability is 3 divided by 10. Let me back up real quick. Do you see what I just did? I just did the multiplication rule again. I did the conditional probability times the probability you just get the second thing. I just wrote them in a different order because this is the order I'm drawing things out of. So this is the chance I draw a red from the 10 balls. And then I'm doing it without replacement, which means now I'm going to take a ball out because my red ball's out. My red ball's out here now. Now there's only 9 balls, and 2 of them are red. And there's 9 total. So the chance that I draw a red ball, given that I've already drawn a red ball, is going to be the chance of getting a red ball out of this group now, which is going to be 2 divided by 9. Now I think that's intuitive. I think that makes sense with the visual. But I want you to see the difference when I do it with replacement as opposed to without replacement. So without replacement, my chance of getting the red ball the first time is 3 out of 10. The chance of getting another red ball is going to be 2 out of 9, and I can compute that probability. I would just as soon do it in my calculator. And I'm going to write it using parentheses, just like I did on paper. So 3 over 10 times 2 over 9 is going to be 0.0667. That's how I'll write that. 0.0667. So that's my chance of drawing a red ball and then drawing another red ball with the red ball already not being replaced. So now let me put the red ball back and, oops, oh, all right, there it is. And now I'm going to do the same thing, drawing with replacement this time. So if I want to get a red and a red. That's going to be the probability that I draw a red times the probability that I draw a red, given that I just drew a red, and put it back. So you'll see this is not really a conditional probability after all, because I'm putting the red ball back. Okay, so the probability that I draw a red from the group is going to be 3 out of 10. And then I'm going to replace it. So I'm going to put it back. So imagine taking that out and then putting it back. And now for the second draw, the urn looks exactly the same as the first draw. There's 3 red balls. There's 10 balls total. So the chance that I draw a red again after drawing a red the first time, well, this is just the chance that I draw a red, period, like the first time. This number is actually going to be 3 out of 10, just like the last number. So it doesn't change. You see how these are independent now? So this second draw has nothing to do with the first draw, because even if I drew a blue ball in the first time and put it back, the second draw is going to be like I'm drawing from the regular population altogether. So this is what we mean by with replacement being independent, because the second draw ends up looking just like the first draw, and as opposed to without replacement being dependent, where the second draw entirely depends on what you get the first time. So if I were to draw a green ball the first time, this number would still be different than it is right here when I replace it. Let me do this in my calculator real quick. So 3 over 10 times 3 over 10 is going to be 0.09, which is a little bit bigger, than this one. And that actually should be bigger, because in the first draw I've got 3 reds, and the second draw I've got 3 reds, whereas here the first draw I have 3 reds, the second draw I only have 2 reds left, and there's only 9 balls left, so that's a little bit smaller than 3/10. Okay, so this is to show you that in this little example, the difference between sampling with and without replacement, and how sampling without replacement gives you something dependent, where you've got your conditional being different, and sampling with replacement being independent, where your conditional doesn't really exist. It's just the chance of drawing the red ball the first time. Being able to distinguish between whether your events are dependent and independent make all the difference when computing these and probabilities. And that's kind of the point of this video. So your job is to determine whether, when you're doing and probabilities, determine whether or not they're independent, and then letting that affect which version of the multiplication rule you use.